你是穿这个衣服，你是穿这个衣服。啊，这里还有同学里面有各种搞笑，都很有意思这样。有啊，应该有。啊，对，好，哎，我是我们要去地区，天牌，他是天牌，我感觉，哎，有点，抱歉啊，抱歉，你上次又不看了，你还有放这里？那我感觉你跟上次的是这个，第三个，应该是一个是做一个，哪个？神奇，一个神奇。你上每一个每个节点都跟一模一样。我都不知道啊，因为我跟那写过就是我之前不老直接把一个删，然后有再给我那个我没有找过这见过。真的一模一样，他找你们不知道。我连我自己都不知道，我自己来我是谁打人的。然后客房是床非常好看啊，真的。前一般可是一个我们上的每一个都需要，seriously，真的，一模一样。这个你上一个班的时候，他就你上完这个吗？还是下午今天早上只有上完这个？你可以看你用你可以看你一模一样。他可是这个人是谁打人的是？我像是你现在要上那个你上那个，这个要怎么？我看到你滑到你现在上的，那个我很明显是送你。我不知道，给你找。对我讲找资料能力很容易的。我操！我操！我今天穿进这个，故意有啥？但是哦，我本来想打算要选这个先，还是再选这个，然后我会先听这个。我还想听这个，因为很好听。可以，都是这个。要不那个高细分的人。哎，真的这本书好像更难。来给我这本书，我有找啊，中国高3000。这几年的书我感觉很老。去年的。啊？可是他的那个就。
Seng给我这里 ，nice，对，是吧？是啊，是啊，是。我是有带，很多呀，这里面还没有吃，我在家。好东西我还是慢慢吃。
2018是第一个 edition，然后July 2019是第二个 edition。2018中国多少地方都没事了。Hello, testing. Okay, good afternoon to everyone. So yesterday I made an announcement, right, in the assignment question for part 2. When you prove monotone convergence theorem imply completeness theorem, completeness axiom, right? You can just write whatever you can. You don't need to provide the full detail, and I will give bonus mark. Okay, if you try and do it. Yeah. Because it turns out that the detail is quite tedious. Okay, but I will write down the detail in the solution. Now you can read later. Okay, just roughly tell me how you make a sequence, then how you get the limit. That's enough. No need to check properly. Okay, because there are quite a few details to check if you need to construct the full argument. Okay. Okay. Sure. So any question from yesterday lecture or tutorial question or not? How to prove infimum, supremum? Yes. Yeah. Yeah. You need to propose one first. Yeah. Only you can start the calculation. Right? Otherwise, it might be hard to just randomly bound stuff. Might be hard, but not to say not doable. But yeah, propose a number and then see if you can find the bound within epsilon. Then if you can do it for all epsilon, then it converges. Okay. Actually, I want to ask how rigorous you guys did in calculus 1. Because I know that epsilon definition also introduced in calculus 1, right? So do you guys do question on this or not? Question or question? Is it similar to what I have in the last question? Okay. Only one. Continuity or sequence? On continuity. Oh, okay. Yes. On continuity. Okay. Sure. I see. Okay. So today we will continue to talk about sequence. Okay. There's a new type of sequence we want to talk about. It's called the Cauchy sequence. So Cauchy is a person, mathematician. Cauchy. Okay, so
What's the motivation of Cauchy sequence? So let's say we want to look at one convergent sequence here. Let me give you one sequence, and I'll ask you. Do you think this sequence conversion? Yes or no?
Yeah.
Why? How you think that this sequence converge? Seems bounded. Seems bounded. Remember this, so you think this is bounded, is it? Seems bounded. Why you think that this is bounded? Do you think that the number is getting closer and closer to each other between the next term? For example, I give this relation here. Is it they're getting closer to each other every two terms, right? But remember, you have this graph, this function here, fx equals to square root x. How does this graph look like? How does this graph look like? Also like this, right? If you take the sequence, also getting closer and closer. But you can prove that, you should prove the sequence square root n converge to infinity. Yeah, no? Doesn't converge. Okay, so this is not a strong condition to check whether sequence converge or not. But what kind of sequence is converging? So let me give you a definition here. Sequence an is a Cauchy sequence if for every epsilon greater than 0, okay, this should become a chant already. So after you get the epsilon, what you need to do? Find what? Find what? N, right? Find some natural number. Okay, such that, okay, now this time is a bit different. Such that any two number greater than this n here implies that the distance between am and an is less than epsilon. So this one is stronger than what we had just now. Right. Here is for all the m and n behind the capital N, the distance is close within epsilon. Can you imagine what is this thing doing or not? Once you set the epsilon gap, everything, the distance between everything behind, have to squeeze down into the epsilon. Just now, we only squeeze 2 by 2 consecutive term within epsilon. Okay? Can you imagine what I said? Imagine or not? Okay, so let me try and draw if I can. So you see, this line here, what does this mean? For every epsilon, right? For every epsilon, you can get all the terms, all the consecutive terms squeezed between epsilon. So how should I draw this? This every two. Okay. Every two squeezed between epsilon. Okay. But what does this Cauchy sequence do? For every epsilon, okay, for every epsilon, so for every epsilon, I can squeeze after n epsilon all the terms, all the two terms here, any two terms here is squeezed between epsilon. I squeeze a whole chunk of them within epsilon. But previously, I can only squeeze 2 by 2. Okay. Yeah. Here is the difference of consecutive term. Okay, but here all combination. Okay, all the differences after n epsilon. Okay, everything I squish with epsilon. Okay. Yeah. Does it make sense? Okay. So next theorem we're gonna prove is a sequence an is Cauchy if and only if it is convergent. Okay. So we will prove this. If the sequence is Cauchy, then it is if and only if it is convergent. Okay. So let's prove it. So let's do the direction from convergence to Cauchy. Okay, if you converge to some limit, you should have this Cauchiness here. Okay. So let's put down what we want to show. What do we want to show? What is Cauchiness? For every epsilon greater than 0, there exists a n. Okay, there exists an n such that two numbers mn greater equals to n epsilon implies that the absolute value of an minus an is less than epsilon. Okay, everything behind n, the difference between them is less than epsilon. Okay. So meaning what? Given an epsilon, so you need to fix any epsilon greater than 0. Want to find an n such that this is true. So there's really only one condition you can use here is this an is convergent. Okay, this an converge means what? Converge means what? Sorry? No. Converge means bounded, yes. But what's the definition of convergent? For all epsilon bigger than 0, there exists an n such that when n greater equal to n, an minus l absolute value is less than epsilon. So what is that L? It's the limit of the sequence. Okay. So we can only have this condition here to use, right? You see, there are really only two things inside this statement. So if you want to prove Cauchy, you can only use convergence. There's nothing for you to play around. Okay. So fix an epsilon greater than 0. There exists an n depend on epsilon. So let's call this NL epsilon, such that when n greater equals to n epsilon, implies that an minus l less than epsilon. Okay. Okay, so this is what you know. So how do you relate an minus l to an minus an? How do you relate the two? And then what do you mean? Why do I want to add epsilon up? I'm asking about difference between a minus an and an minus l. Sorry? What is? What do you mean by that? What are you trying to do actually? Huh? Yeah, so how do you use what you have here to prove this inequality an minus an? Yes, use the triangle inequality. So what's the triangle inequality do? I can bound the difference between am and an by what? Okay, so really we can introduce the term minus L and plus L into the expression first, right? And then I can split this terms out in using triangle inequality, right? Make sense? Okay. So in principle, we can do epsilon plus epsilon, okay? But to make it nice, we can use epsilon over 2 plus epsilon over 2, which is epsilon. So meaning we can use epsilon over 2 for these conversion of an, and then what is the n we can pick here? Really, for this equation less than epsilon 2 to whole, we need to pick the n epsilon to be the n L epsilon over 2. Okay, then the calculation will hold. Does it make sense? Okay. And Roland come to my office hour, ask me, hey, why we need to calculate the calculation first, and then we pick, then we decide what we pick. But we write down what we pick first and we only calculate. Do you all have this kind of problem or not? Why when I try to find the n, I do this calculation first. But when I write the proof, I write n first. Did you guys get what's the problem? Huh? Can you understand what I said? Right. Because this is about logic. Okay. Logic is for every epsilon, you want to find an n such that the calculation works. But you are in a real life. Your real life means what? You need to make sure the calculation works first. And then you know what to fix. So you start with what you want first. This is my point. Okay, so every time when I ask you to write down the proof, I ask you to write the goal first. Because the goal will remind you what to calculate first. After you write down the goal and then start with what you have. Okay, does it make sense? Okay. Okay, so in the actual proof, right, they will just write it as an essay. So I have this, so I have this. Okay, it doesn't tell you where I have to go first. No need to tell you because you will see it after you read the whole paragraph. Okay, but when I teach you or when I write my lecture notes, right, often I will say what to show first. I need to know where I go first. Okay, then I start what I have, and then I got this, so I got the final answer as desired. Okay, as I like, as one wish. Okay, does it make sense or not? Okay. Now still got people ask about why we choose epsilon over 2 or not. Any question? Any people? Anyone confused why we use epsilon over 2 here? Anyone confused? I can use epsilon over 3 also. 2 over 3 epsilon also can. Yeah, but I cannot use epsilon plus 2. Cannot do that. Otherwise, you just bounded by 2, not bounded by something getting smaller and smaller and smaller. Okay, it must be epsilon times something. If epsilon plus something, then you can only show it bounded by that extra stuff. No use. Because we want to make it bounded by every epsilon so that this term here is bounded by any number smaller. Okay, so we get that A n is Cauchy. Okay, so every convergence sequence must be Cauchy. Okay, how about the other direction? If it is a Cauchy sequence, okay, how to prove the convergence? Okay, if it is a Cauchy sequence, how to prove the convergence? If it is a Cauchy sequence, how do we prove convergence? Okay, we will split into two parts. Okay, we split into two parts. So first, we'll prove that every Cauchy sequence is bounded. and bounded above and bounded below. And remember, a sequence is bounded above and below. What do we have? We proved for 2 lectures already, both done on workshops. If you have a sequence that's bounded, then you can find a convergent subsequence. Okay, remember the picture I draw in the class. Any sequence in the bounded interval, I can find convergent subsequence. I use vista point or I use the pigeonhole principle. Okay. Next, so more importantly is a Cauchy sequence. So by Bolzano-Weierstrass, I know that this Cauchy sequence has a convergent subsequence. Then I will use this convergent subsequence to show that my Cauchy sequence is actually convergent. Okay. So what does this mean? You have a Cauchy sequence. Okay, you know that for every epsilon, all the 2 terms behind the capital N getting close within epsilon. Okay, but you don't know yet whether the limit exists or not. So how do you find the limit here? The strategy here is I go to the Cauchy sequence. Okay, I go and find a convergent subsequence. So convergent subsequence has a limit, right? So we try to show that this limit actually is the limit of Cauchy sequence. Make sense? Okay, no? Okay, so this is the strategy. Okay, so I let you discuss with your friends first how to produce these 2 statements. Okay, actually, the first one is quite related to every convergent sequence is bounded. Try and discuss with your friend how to prove this 2 statement here. Okay, we will resume 5 minutes later. Okay, try and discuss with your friend how to prove this 2 statement. Actually, it's very related or using what we have done. I let you discuss first.哎，什么叫我啊？都有问题。是。最厉害的。 That's it. Which one? Oh, okay.
我要考察一下的表达能力。他笔测是我讲的题。等一下我就。
Okay, almost done. Okay. Like, so what does it mean by every Cauchy sequence is bounded? Yeah, what does it mean by every Cauchy sequence is bounded? If an is Cauchy, then there exists an M in R such that what? No need larger, I need to bound everything, right? So every n, okay, every n. For every n, absolute value of an is less than or equal to m. Okay, this is what you need to show. So how to show this? How to find this m? How to find this m? Okay, we want to find this m. How to find this m? But remember what's Cauchy? Cauchy says what? Again, definition. I like definition a lot, so you must remember. So what's the definition of Cauchy? For every epsilon greater than 0, you can find a natural number such that everything, every two terms behind these natural numbers, the difference is less than epsilon. So what does this mean? I can control everything at the tail using this kind of no. So let me write down the definition again. Suppose an is Cauchy, then for every epsilon greater than 0, there is an n in n such that for all mn after n epsilon, the terms am minus an, absolute value of them is less than epsilon. So how do you imagine this? So I got some sequence, okay? I got some sequence. When I talk about sequence, pull out this x-axis, okay? And then all the sequence behind n epsilon. So we need to fix some n epsilon here, okay? And then all the am and an. So am and an, something like this. Am and an. Everything behind it. Correct or not? For example, here is n epsilon plus 1, n epsilon plus 2, n epsilon plus 3, for example, right? And all these guy is what? Is within epsilon. Okay, is within epsilon. So I should draw like this. Epsilon minus epsilon. Okay or not? Okay. So meaning what? The tail I can control. I can control the tail of the sequence. What happened before n epsilon? What happened before n epsilon? What happened before n epsilon? It could be someone inside and also someone outside the gap. Okay, but there are really only finitely many of them. How many of them outside here? At most n epsilon minus 1. So can you find the bound or not? Can you find the maximum and minimum guy or not? Okay, so we can just pick which one is the largest one. Okay, because all the thing at the tail we can control by epsilon. Okay, so let me write down this proof here. So in particular, we can fix epsilon equals to 1. Okay, then there exists. Okay, then there exists what? Exists and n epsilon 1. Okay, in n, such that for all the terms, all the two terms behind n1, we have the absolute value difference less than 1. Okay, I control everything within 1 at the tail. So in particular, what? In particular, recall the inequality we have last time. We have absolute value of an is less than or equals to the absolute value of an plus 1, an1 plus 1. Does it make sense or not? Okay. Does it make sense? No, make sense? Okay, where? Which one? Which line to which line? Last line, huh? Okay, last line. So what is an minus am? So let's say, imagine again. Okay, let's imagine again. So now we pick a real epsilon now. So we pick real epsilon as 1. Fine. Okay. So let me do this. So 1 and minus 1. Something like that. Okay. My an and am live where? So let's say we fix my n1 here. Okay. So n1 could be here. And all the things behind maybe sit away around here. Maybe sit away around when maybe like this, like this, like this. An maybe here. Okay. Every m and n behind. So m here and n here. Does it make sense? All the mn behind n1. Okay. Is within this bound here. Okay. Is within this bound here. But why I can do this? Why can I do this? Okay, so let me draw another picture for you. So what is this difference here? An minus am is less than 1. What does this mean? So maybe I fix an first. Okay, an. Where is where is am? So am can live in the region plus 1 from an or minus 1 from an. So am could be somewhere here, or am could be somewhere here. Is it true? True. True, right? Okay. So an could be somewhere there or somewhere below. Why become like that? Okay. So meaning what? This term here is the top. Okay, so this term here is the top. So what is this term here? So here I claim that this term is really an1 plus 1. Why is it true? Sorry? an1, an1, yeah. Is the term, the first term that you can realize this inequality here. Okay. So an1 is the first term that do this. This is how we find the an1. Okay. And then an1 plus 1 should be here. Bounded above by this term. Okay. Why we put absolute value? Because this an could be negative. So if we place as a modulus, then it is always the top guy. I think I proved this in one of the lecture. Let me see whether I proved this or not. Okay. Yeah. I think I included this proof. I'm not wrong. I remember we talked about this one time. Anyone remember we talked about this inequality here? Yeah, this one. Okay, actually I included this proof here. So this is the proof of the statement. For every AB, okay, in real line, the absolute value of A minus B, if it's less than some positive number, then I have this inequality. Okay, and why is this true? I use this property here. A less than equal to B if and only if AP is less than equal to BP. Yeah, this is the proof. You can try and look at this. I remember we talked about this inequality in class last time as well, but we didn't really prove in class, so I supplied it in the lecture notes. This is lecture 7. Yeah. Yeah. Strictly less than. Let me see. Do we have strictly less than there? Oh, sure. Yeah, I think we can put strictly less than. Yeah, because if you prove less than equal or less than or equal, if it's just strict, still okay, because it's all right. So one true is okay. True or false is true. So sometimes will be a bit sloppy. You know what's sloppy? You know what's sloppy? 有点粗心. Okay, let me. So just now, Joshua asked if A is strictly less than B, right? Okay, why I put A less than equal to B? But I said that this is true because this is less than or equal. So meaning if just less than true, this one false, still true. Okay. Yeah, so we will sometimes a bit sloppy. Okay. But if you want to throw away the equal signs. Make sense? Okay. Okay. So how do we choose M here? So how do we choose M here? Therefore, for all n in n, we have the absolute value of an less than or equals to m, where we choose m to be the maximum of who? Maximum of this guy, an 1 plus 1, or some terms that is outside the epsilon gap. So what are the terms outside the epsilon gap? Those are the a1, a2, dot, 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 up to a n1 minus 1. Okay, these guys are potentially outside the epsilon gap. Okay, so we choose among these. I can pick the maximum one because there are only finitely many of them. Okay, in particular, there are only n1 of them. Okay, makes sense? Question? Question? Any question? Actually, this is the same proof we use to prove every convergence sequence is bounded. Same proof. Okay, it's the same proof. Every convergence sequence is bounded. No question? Can we continue? Okay. Let's continue first. So what? So by Bolzano-Weierstrass theorem, an has a convergent subsequence. It has a convergent subsequence. Let's call it a name. So let's call it a name. Call it a name. Let's call it AJN. Okay, last time we said that we introduced the increasing function J, okay, to represent our subsequence. Okay. Now, since it is convergent, right? Suppose AJN converges to a limit L. Okay, suppose it converges to a limit L because it's convergent subsequence, right? Converges to a limit L. So this means what? Again, what is the definition of limit? What's the definition of limit? Ziying. What's the definition of a limit? Yes. Convergence. Start with epsilon. Epsilon. For every, you quantify. For every, okay, that exists, okay, and let's call it NL epsilon in N such that小n 小 n 大于等于 n epsilon L implies AJN L 的 absolute value 小于 epsilon。OK， yeah，一直念念到 week 15为止。OK， 一定要刻进去。OK， so you have this convergent limit here. So we want to show that Cauchy sequence converge. How? So we want to show that. Want to show actually AN also converges. So here we claim, okay, this is what we claim. We claim that AN, the Cauchy sequence actually converges to L2. Okay, to L2. Converge to L2. How to prove? OK， 下一个再问你不是 ？OK， 什么叫做 AN converges to L？ 喂， Yeah. 是，但是我要 definition。再来 epsilon，快点 epsilon， 每一个啊，讲看 exist n epsilon in n such that implies 没有 AJN， 现在不是 AJN，AN 罢了，小于 epsilon。So you see, you got AN minus L, you got AJN minus L. Okay, so how you use AJN minus L to prove something for AN minus L? How you connect? How you relate the two? Max of what? No. You see, so this n here is given. Okay, this n here is you want to find. Okay, one n is what you want to find. One n is given. So how? So you need to use the working, right? Working first. So how do you make sure AN minus L is less than epsilon? Can you somehow use AJN minus L or not? How? Again, this trick, you must never forget, analysis like this trick a lot. A lot to the power 100. Okay, so you can introduce the extra term, AJ minus AJN plus AJN minus L. Okay, then what do? Again, triangle inequality. AN minus AJN plus AJN minus L. Okay. Not that you can make this final term less than epsilon because it converges, right? But how about the first two? How to do here? How you found this? Cauchy. How to use Cauchy here? How to use Cauchy? Always greater than n. Less than n? Greater than n. Increasing, right? Yeah. And then, so how to use the Cauchiness here? What do you have? Okay, so you need to introduce the Cauchiness. So here is the Cauchiness of AN. And then this part is the convergence of subsequence of the Cauchy sequence AN. Okay, so you see there are two n controlling here. So one n is controlling this convergence subsequence. The other n have to control the Cauchiness of the sequence. So you need to choose the maximum between the two. Okay. So since there are two of them, right? So we like epsilon over 2 here because when they add out, they become epsilon. Okay. So what? So let me see how we write this. Okay, so let's write this down. So this is working. Okay, so working done here. So we know we need to pick maximum between this two n. Okay, so let us fix here. Okay. So now, we prove this claim here. Proof of claim. So you need to show for every epsilon. So you now fix a epsilon greater than 0. Okay. And there exists n epsilon c. Okay, we call it a c. Why? Because we're gonna use this to control the Cauchiness of my sequence. Okay, we use this to control the Cauchiness of my sequence. So everything behind n epsilon, an minus an is less than. Okay, we control the Cauchiness, but we want to control within epsilon over 2. Okay, we want to control within epsilon over 2. Then what we choose as our final n epsilon here. Okay, our final epsilon here is chosen with maximum of this Cauchiness nc epsilon over 2 and the convergence of the subsequence nl epsilon over 2. Okay, so this is what we wrote down just now. Okay, nl is the one for ajn to converge. Okay, then what? Then for jn greater than n greater than n epsilon, what do we have? An minus L is equals to an minus ajn plus ajn minus L, and then we use triangle inequality to split out the sum. And then for n large enough, okay, we can control the first term by just epsilon over 2, and for n large enough, I can control the term, the second term within epsilon over 2, and then epsilon over 2 plus epsilon over 2 is epsilon. Okay, so we are done. Okay, so since epsilon greater than 0 is arbitrary, okay, we just fix any epsilon over 2, epsilon. This proves what? This proves that an converge to L. Does it make sense? Make sense or not? Does it make sense? Any question? 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 Okay. Okay. All right. So before we leave this Cauchy stuff, I want to comment a bit about Cauchiness and completeness. Cauchy sequence and completeness, or the completeness axiom. Okay. Cauchy sequence and completeness axiom. So for every irrational number, right? Okay, if it is irrational, let's put this as I. Okay, let's put it as I irrational. I can construct a Cauchy sequence of rational numbers that converge to Q. That converge to what? I. Okay. How to build this Cauchy sequence? Do you have any idea? I said there exists one, so it's possible to create one. So do you know how to create this? I claim that if you take a irrational number, what are the irrational number you know? You also can take square root 2, okay, whatever you like. I said that there's a Cauchy sequence of rational number that converge to this irrational number. How? Can you think of a quick way to do this? So you take the decimal expansion, okay, of your irrational number to n digit. For example, okay, who can remember what's the pi? The decimal expansion of pi. 3.1418159. Okay, so Your first term in your sequence is 3. Second term is 3.1. And then third term is 3. Yeah, so let's write down. So 3, 3.1, 3.14, 3.141, 3.1418. These are rational, right? Oh, sorry, 15. Okay. So these are rational, right? Because you can write, for example, 3.1 is what? 3/1. 31/10, right? And then this one is 314/100, right? And then these are really rational number, correct? Okay. So I claim that this number is converging to irrational number. Okay. The limit is irrational number. Okay, you use the f for every epsilon, and then you find an n such that for every n greater than n is less than epsilon. Okay. So what I want to do here is I'm trying to say that every irrational number is a, so I put here, so every irrational number is a limit of some Cauchy sequence. Okay, every irrational number is a limit of some Cauchy sequence. Okay, so you see, if your set is just rational, right, you might converge to something outside the set. Okay, you might converge something outside the set. So we will introduce another alternative completeness axiom, which is every Cauchy sequence of real number converges. Okay, so this is another way to think about real number. So your real number split into rational and irrational. Okay, so how should you think about this irrational here? They are the limit of sequence of rational number. Okay, so this is another equivalent formulation. Okay, formulation of real number. Okay, so if you want to ask, you can ask whether this is equivalent. Okay, whether is this equivalent to completeness axiom or not. Every non-empty bounded above set has a what? Has a least upper bound. Okay, is it equivalent or not? Okay, it turns out that you need this axiom plus Archimedean property, only that this is equivalent to the completeness axiom. Okay, only this is equivalent to the completeness axiom. So in the assignment, what you have did already, you show that completeness axiom is equivalent to monotone convergence theorem. Okay, and it is again equivalent to this formulation of the Cauchy sequence formulation of real numbers. Okay, so in some sense, you can think of this irrational number, right, as equivalent classes of convergence sequence. Because why? Because just now, right, this is just one of the example you can take to converge to where? To pi. Pi, right? Okay, converge to pi. Maybe you can have other Cauchy sequence that converge to pi as well. Okay, but all of them have the same limit pi. And we will say that they live in the same equivalent class if they have the same limit. Okay, so you can think of an irrational number as a bunch of Cauchy sequence that converge to the same thing, but the Cauchy sequence are different. Okay? So this is another way you can think about number. So make every number into a sequence. A sequence of rational number. Okay. 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 So how many ways we think about irrational number already? The first way we think about it is using what? Least upper bound. Okay, we show that soup of the set must exist and then it is equal to square root 2. Remember? Okay, soup of some set. Now I make the soup into sequence. Okay, like what you did in your assignment. Make it into non-decreasing sequence, for example. But here we make it into Cauchy sequence. Okay, Cauchy sequence. And then irrational number is the limit of some Cauchy sequence. Okay, so these are few ways you can think about numbers. Okay, make sense? Okay, there are few ways to think about numbers now. You can think about number as a set, supremum of a set, or you can think of it as a limit of some sequence. Okay, Cauchy sequence in particular. Yeah, no? So number is not just number. Number represents some huge stuff. Right. Number represents huge stuff. One table is one. One chair is one. One person is one. One tree is one. One classroom is one. One school is one. Why one can represent so many things? Okay. So these are all different ones, but they have some similar property that go between them. Okay? Does it make sense? Okay, no? Okay, so this provide a new way to think about real numbers. Okay, and quite convenient sometimes. Okay, quite convenient sometimes. Yeah. Yeah. Any question before we take a break? Any question before we take a break? Any question? Okay, so when you take a break, you can take this snack if you like, again to keep you awake. You can share among you. Right? Okay, let's take a break until 1:12. Okay, 1:12. Smile. Oh, okay. Okay. Thank you.分一下，分一下。 讲台。应该是有很容易的。发现，你看它这边好像一样宽，但是这边特别宽，
特别宽是特别
宽了
特别宽
啊，对，这边特别宽，很有意义。然后我们学习这里挖一挖，
有点数学的味道，但是好像又讲不出来这个关系。
但是我们现在都有省起来，因为它有些是很白痴。那开一杯。
对我来讲，好像人性啊，我也是还没有发现到。
为什么？又去跑？老他有去跑？
没有打定位。
哦，对。
高力，就像你的雷蒙到很多美金。
不打。
或者我让这个什么一起可以描述过来吗？可以描述一下。稍微高一点。其实也跟这个差不多。我就把它。
哎，没有啊，没有人要吃啊？真的吗？
反正肉干好吃吗？
还可以啊，还可以。你说那个火腿呢？
啊，很大。
挺好的。
选一个12点到3点，一个时间差不多。你觉得哪一个？但我选还是不上课的。说嘛，那我觉得3个小时的课很慢，到后面就很难。确实。
提议一下给学校，叫学生会考。
我是参加了。
或者我们玩一些人传，我们以前是这样上课的，10年啊，一家，然后有我们在中学嘛是这样啊，真的是。
去学生会有个利用嘛，其实学生会只会在竞选的时候给你讲一堆，我要什么管理学校，我这个定会，对呀。并且去的话，那个以前我们课是一个表，大学，建议给校长，这就是我们学校不是世界强校的原因，课程时间太长。
确实，提一下。
哦的 attention span 可能到10万毫，所以30分钟就是这个。
什么套？哦，OK，不错，不错。Not bad, not bad. Okay, so let's continue. Okay, before we jump into continuity, about link soup and link if. Okay, remember that last time we talked about this divergent sequence here, which is what? Which is, so let's pull this thing out. So which is -1, 1, -1, 1, -1, 1, -1. So it's the alternating -1 sequence here. Okay. But there's some obvious convergent subsequence here you can see. You can see here. You see a convergent subsequence here. What are the convergent subsequence you can find? All the ones or the -1. Okay, these are the two convergent subsequence. Okay, where the first one you take the even term, and then the second one you take the odd term. So here Bn equals to A2n, and then the Cn below you take A2n plus 1. Right. Okay, or minus 1. If your 1 start with 1. Okay. Okay, so another observation. So here is the observation one. Another observation. So observation 2. So now we're trying to relate the convergence or the divergence to a subsequence. So there's another observation. So how can you determine whether a sequence is not bounded above? How do you determine whether a sequence is not bounded above using subsequence? How you determine? Okay, let's imagine a scenario again. So you have AN, right? AN can be like stock. You know stock or not? Recently, I look at the stock, and then the stock market is like something like this, and then come down a bit, and go out a bit. Okay. So how do you determine whether a sequence is not bounded above? Using subsequence. You see, some terms could be going down, right? But let's say this sequence is not bounded above. What can you find? Or in other words, you can find a subsequent which is strictly increasing. Okay, which is strictly increasing. Which is increasing. Okay, strictly increasing. Subsequence. Okay. And if this sequence is strictly increasing, then this limit have to diverge to infinity. Okay. So this is a few ways to determine what's the convergence or divergence of the original sequence. Okay. So to this end, we will define two sequence first. Okay. Let's define two sequence. Two kind of subsequence. Okay, let's define two types of subsequence here. So let's consider, so given a sequence AN, we can define two kinds of sequence. This two kinds of sequence is very special. Please be a bit alert. So let's call it Bn and Cn. Okay. So how do we define this? For every n in n, okay, what is Bn here? So we're gonna use what is called inf, okay, inf of an, ak, okay. But this k here, we just regard all the k greater or equals to n. Okay, so what does this mean? This means this is the inf of all the sequence such that, okay, such that these terms are all behind n, greater n. Okay, 6 and n, and then look at all the terms behind n, an. Okay. And another thing is we call sup of kn ak, okay, equals to the sup of all the terms behind n. Okay. So in particular, what is B1? So let's look at some example. What is B1 here? B1 equals to what? Inf of k greater equals to 1 of a k. What is this? This is the infimum of ak such that k is greater than 1. This is what? This is really the infimum of the original sequence. Okay. This is the B1 is just the normal infimum. Okay. How about B2 then? B2 is what? I just take infimum among A2, A3, A4, A5, A6, and so on. So I throw away the first term. Okay, so what happens when this n grow? You will throw away finitely many n terms, and then you consider the infimum. Okay, so can you see some trend here or not? Can you see some trend here? What's the trend of B1 and B2? B1 is greater or equal to B2, or B1 is less than or equal to B2? B1 is less than or equal to B2. Why? Why? Yeah. So you would potentially throw away the smallest guy, right? Okay, so your number is kind of, so this Bn form a non-decreasing sequence. Okay, so Bn form a, not that. Bn is less than or equal to Bn plus 1 for all n. That is, Bn forms a non-decreasing sequence. So similarly, Cn, Cn is a soup. Okay, C1 you take a soup of your sequence, and then C2 you throw away the first term, and then you look at the soup again. So this sequence, this form a what kind of sequence? Non-increasing, right? Because you potentially you throw away the largest guy. Okay, so similarly, Bn, sorry, Cn forms a non-increasing sequence. Okay, so you have sequence on your hand, right? So what we can do? What can we do? We can define again the limit of these two sequences. Okay, we can define the limit of these two sequences here. So what's the definition here? So first definition, the limit inferior, or sometimes they call limit infimum, or I think some of the book they call it lower limit, okay, of an, okay, where an is a sequence of real number, and we denote it by let's see, lim. Let me see, how do I write this? We denote it by me get this thing right. I don't want to confuse. Find it to be lim inf. Okay, so let's do lim inf first. Denote it by lim inf, lim infimum, limit to n infinity of infimum of an. Okay, so how does this define here? So lim n to infinity of infimum of an, okay, is what? Is what we wrote as just now. This is a limit of greatest lower bound, right? Of an, comma, an plus 1, comma, or this is really what we have just now. When you take n to infinity of the, what we have bn. Okay, so it's the bn we have just now. Or if I write it out, it's just infimum of k greater or equal to n of ak. Okay, and not that this is a non decreasing, non-decreasing, so it is like increasing or equal, right? Okay, so the limit of this should be the supremum of all these infimum. Okay, a bit crazy, I put sup and inf together. Okay, I first take inf first. Okay, I take the smallest, and then I take the supremum. Okay, because this inf is like growing, and then I can take the sup. Similarly, we can define what we call the limit of superior. Okay, limit superior, or call it a limit supremum, or some of the book will call it a upper limit of an. Okay, and this is denoted by similarly by what? Lim n to infinity of sup an. Okay, so lim n infinity of sup an is what? And there are a few ways to write about this. So it should be the lim of LUB, and lowest upper bound, which is the supremum. When you decrease, when you increase in your AN, where you throw away the first few finite term. And really, this is the limit of the Cn we introduced just now, which is the limit of of sup k greater or equal to n ak. Okay, and so the sup is getting smaller when you throw away the finite many term. So you will converge to inf of the sup. Okay. You take the smallest among all the sup. Okay. Yeah, so this is a lim sup and lim inf. Any question about this definition? Definition got question or not? Okay. If not, let's go into discussion. Okay, let's discuss about 4 sequence here. Okay, so first is 1 over n. Second is an equals to n. And the third one is an equals to -1. And the last one is an equals to -1. And 1 plus 1 over n. Okay, so for all these questions, try and find what is inf of inf. Let me write down. Find what is inf of k greater or equal to n of ak, where k is greater or equal to n. Okay, so this is what we call the bn just now. And also cn, what's the new sequence you can get here? Okay, and then find what is the limit of bn, and find what is the limit of cn. Okay, so let's break into groups. So 1, 2, 3, 4, 5, 6. So let's say we have 6 groups here. So can we like form like 1 row, 2 row, 3 row, 4 row, 5 row, 5th row? Okay. So you guys will do 1, 2, 3, 4, 1 first. Okay. Does it make sense? Yeah. Discuss among row. Okay. 1, 2, 3, 4, 5. And do 1, 2, 3, 4, 1. Okay. Yeah. You start with the question we assign first, and then if you finish, then discuss the next one. Okay, find these 4 values here. Vn, Cn, limit of Vn, and limit of Cn. Okay, yeah, start. Give you 10 minutes, 5 minutes, 10 minutes, yeah, 10 minutes. Try and find what is BN, CN, what is limit of BN and limit of CN. Hmm? Hello. 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 Okay. Let's try. Okay. So this definitions here what include what? It tests you whether you know how to find infiniment or not, how to find supremum or not, and then whether you can find the limit or not. Okay, three things. Okay, these three things put together. Okay, put into this definition. So what is an equals to 1 over n? Whenever you have sequence, right, pull your R2 out. Okay, and then plot it. So you have 1 half, 1/3, 1/4, 1/5, 1/6, so on. Okay. So who do question 1? What is Bn? In particular, what is B1? B1 is what? B1 is the infimum of An. Right. Okay, so what's the infimum of An here? This is what we have proved, right? Infimum of 1 over n, the set of 1 over n is what? Is what? Converge to what? 0. Okay, how we prove this? Use the Archimedean property. Okay. How about B2 then? B2 is what? All the terms except A1 also converge to 0 because the tail converge to 0. So similarly, you can prove that maybe by induction. Okay, by induction, maybe you can prove that Bn is really just 0. Okay, by induction, you can prove it. How about Cn? How about C1? Supremum, okay, of this 1 over n is what? It's the first term, right? Okay, it's A1. A1 is 1. But if you throw away the first term there and then look at the supremum there, n greater than, sorry, k greater than 2. Yeah, so what do you get? A half. So you can prove by what? You need induction in this case. Do you need induction? Maybe you don't need induction, and then prove that Cn equals to Cn is really equals to 1 over n. So you can see Bn is a sequence 0. Cn is a sequence 1 over n. So you look at their limit here. Okay, limit of inf of k greater than n is just 0. Okay, and then limit of, what am I writing here? 0. And then limit of sup of k go to n of ak. So here's ak is what? What's the limit here? Is what? Limit of the sup of ak is what? Limit of 1 over n is what? Limit of 1 over n, why is it 1? 0, right? 1 over n converges to 0. Okay. So you can see that this lim if and lim sup is equal. Okay, they are equal. Can you see or not? They are equal. They are equal. And what? And what's the original limit of this sequence? 0 also. Not a coincidence. Later we'll prove it. Okay, not a coincidence. We will prove it later. Okay, let's look at another example. An equals to n. Okay, what is Bn here? So what is infimum of k greater than equal to n of ak? What is this infimum here? What is B1? The smallest one. What is this graph? Plot it out, plot it out, plot in your book. First term is 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay. So what is the B1 infimum of this set? What is the infimum of the set? 1. If you throw away the first term, what's the infimum again? 2. Throw away the first two terms. 3. So infimum of k greater or equal to n ak is just n. Okay. How about sup of k greater or equal to n ak? What's the sup? What is the sup of this whole sequence here? Infinity. If you throw away the first term, then still infinity. Or throw away first two terms, still infinity. So you need to prove it. Okay. So for every sup you get infinity. Okay. You need to prove. You need to prove it. If you don't get what I say. So limit of these two guys what? Infinity, right? Just infinity. So diverges. So confirm diverges. And confirm diverges. Link sup, link if diverges, original sequence also diverges. Okay. Okay, good. How about this? The sequence that we mentioned in the start of class, which is this alternating -1. Okay. So what's the inf of n greater than k, ak? 3. Let's change it. K greater equals to n. K. Okay, so what's the first inf here? -1. Okay, if you throw away first term, what's the inf again? -1 again. Okay, because inside your set, really, what do you have? You just have two numbers, 1 and -1. So if you want to look for inf, it is -1. If you want to look for sup, it is 1. Okay. Really, in this set, you only have -1 or 1. Okay, so you have -1 for your inf, you have 1 for your sup. Okay, so you see, this 2 is the subsequence that we pick up just now, right? These two sequence is the subsequence that we pick up just now in the start of class. Okay, so actually they are the inf ak and the sup ak. So limit of inf of ak is -1. Limit of sup of ak is 1. Okay. And what's the original limit of this sequence here? Diverges. So you see, they are lim if and lim sup and is different. Okay. Okay, finally, last one. This one. This one, how to plot? This one, how to plot? A bit challenging. Little bit challenging. So the first term is what? 1 plus 1 over 1 is 2. But you have a -2. Okay, so let's try a -2 downstairs. 2, 3 over 2. 3 over 2 go up. 3. -4 over 3. So slightly above -2, right? What else? 5 over 4. Sure. Okay. Slightly below, right? Okay, so what can you envisage here? What can you see here? It's alternating, but it is like converging to something. Is it to 0? Not sure. You sure? -1 and 1. Okay, -1 and 1. Yeah, that one more accurate. So you might be envisaging that they converge to 1 and -1. All right. So here, right? So what is the inf? So what's the inf of can we find the inf? Can we find the inf? Can. Okay, so let's try and find what is the inf of AK. What is this? The first smallest one is what? The first smallest one is what? So let's start with 1 first, huh? Okay, -1. The second smallest one, eh? So you throw away the first term, right? And then look at the smallest one. -4/3. Okay. But if you look at the which one? Let me think. So first one, you look at everything. Second one, you look at this thing. And then third one, you look at this terms again. So inf of k1. This is what is okay. K greater or equals to 3. AK is what? Again, -4/3. Okay. Okay. Is it true? True, right? Okay. So what's this term here? What's this what's this series here? What's this sequence here? Sorry. What's the sequence here? What's the sequence here? Sorry? Increasing, sure, increasing. Okay. But this sequence here is following what pattern here? Is there a way to write this down? I think there's a way to write this down. Do you want to do that? Do it, huh? A bit technical, huh? Okay, like so increment of k greater or equals to n of ak, okay, should be what? Should be minus or -1 plus 1 over n and 1 plus 1 over n, where let me think how to write this. So sure, okay. So I will define slightly different like this. So -2. Okay, so not like this. So let's do it this way. So okay, let me think a bit. So you see, so let me show you what is my thinking process. Here is for 1, here is for 2, here is for 3. Okay, so how do you think about this? You see, 2 and 3 is the same. So most probably 4 and 5 should be the same as well. You know why? Because you are like considering this set and then considering this set without the first term. So you will, okay, sorry. So you considering this, which set? I do it a bit stupid thing. Wait, let me think. So the first term here, we're considering every term, right? Greater or equal to 1. Okay, we haven't thrown anything. And then the second term, we throw out the first terms here. Okay. And then we will get the smallest one, which is the next smallest one. Okay. And we throw again the next two, the first two terms. So we still left with these terms here. Okay, so we will keep this term. Once I throw away this term, I will go towards another next negative term. Correct, no? So this is what? 6/5, -6/5. Okay. So you are kind of like repeat twice the negative number. Okay, so how do I index this? So how should I index this? So it is -1 plus 1 over n if n equals to 1 and n equals to 2k. Okay, so I pick up the even guy. So I pick out the even guy here. Okay, I pick out the even guy, 2n for some, and so for some k in natural number. But how about the odd guy? Okay, how about the odd guy here? How about the odd guy here? So the first odd guy here is what? K equals to 1. which is the k equals to 1, n equals to 3. So it's this guy here, 3. So how do I get this 3 here? So I just sub into 3. Yeah, good. I think this works. Okay, so this is my sequence. Okay, so this is my sequence. Correct, right? Everyone can check, help check. I repeat when the term is odd. Okay. Okay, in this case here, what is this limit? What's this limit here? What's this limit? -1. Okay, so the limit of this guy is -1. Okay, this is what you guess from the picture, or you guess from the picture and the formula. Okay, this matches out what you have, what you are thinking just now. Okay, so similarly, you can show that the soup of AK is a subsequence that converges to 1. Okay, you can do it similarly. I think we just keep it. It is kind of similar here. Okay, it's really similar. Can you imagine or not? It's similar. Okay, so if you take out, so let's quickly run through verbally. So if I take the whole set, I look at the soup, which is the soup with I take here, is the second term here, right? Because all the other after terms are decreasing. Okay, and then if I remove the first term, who is the largest one? 3/2 again. Okay, but if I remove the first two, what's the largest one? The next larger guy, which is 5/4. Okay, if I remove 3 of them, then what's the largest one? Still 5/4, and then you just pick up the top positive guy as your sequence. Okay, double out, double out, double out, double out. Okay, and then this sequence here is just again 1 plus 1/n, which is converging to 1. Right. Okay. So similarly, I will write here similarly the limit of n to infinity of soup of k greater than n ak is equal to the limit of n equals to infinity of 1 plus 1/n. And this guy is what? This guy is going to be 1. Okay. Okay. So far, so good. Okay. So you can see that lim inf and lim sup are different here. Okay, it's different here. And you can see that this sequence really doesn't have a limit. There's no limit. Okay. No limit here. No single number that all the sequence will get between it. Okay? They are at least, you see, what's the distance between these two? Like, what's the least distance between all the terms here? It is at least 2. At least 2. At least distant 2 from each other. So this is the epsilon gap that you cannot reduce. You cannot reduce. No terms will go into this gap. No. Okay, so it is not true for all epsilon already. In particular, you pick your epsilon to be 1. And you will build this 2 gap. Okay, distant 2 gap. Okay, so why I introduced this? There are very nice, nice theorem here. So first theorem is for any sequence an of real numbers, lim inf an is less than equals to lim sup an. Okay, so infimum an is always less than sup, right? So I mean, let's provide a proof sketch first. So infimum of an always less than equals to the supremum of an. right? Because one of them is lower bound, one of them is upper bound, right? But why once you take the limit, this inequality still preserve? I guess this is the problem. Why? Okay. Okay. Next, next theorem is let an be a sequence such that the sequence converges. Okay, converges. Then this is true if and only if the superior limit and the inferior limit is the same and they are equal to L. So another way to find limit of sequence is through this lim if and lim sup. Okay, look at these two convergent sequence. Okay. Okay, I won't prove this in class. You can do it as an exercise, or maybe I'll put into the next assignment. But I will try and do it in the lecture notes. Okay. Yeah. Try and prove it yourself first. Okay. I'll see if I want to put it into the assignment. Okay, but I also will produce the proof for this. Not too hard, but I guess this one is a bit tricky. This one is a bit tricky. As tricky as the question 4. Because you see, you have something that's always greater or equal to the other term. But when you look at the convergent limit, why this limit still hold the inequality? Why can't the limit go a little bit behind or a little bit after? Why? So maybe you can produce a contradiction proof. Says that y limit of in an cannot be strictly greater than lim of sup. Produce a contradiction proof. If it is cannot strictly greater than, by trichotomy law, it must be less than. Or yeah, but that one is for when the limit is that's for when the limit is finite. Okay, when the limit is infinite, probably is easier. One of them is infinite is easier. If inf is infinite, then most probably the sup of your an also have to be infinite. Okay, and then if sup is infinite, I don't need to prove anymore. Because anything is less than or equal to infinity. Okay. So the tricky part maybe is when both of them is converged to a finite number. Okay, I think this is as tricky as the question before. Try and think about it, and then I'll try and write it out. And then let's see if we want to put it into a separate. Okay. Okay, any question about this lim if and lim sup? Wow. I think we spent about a semester. We come back to this story again. Remember the first time I told you guys about this -1 thing. The first day I talked to you, I said that there's some convergent sequence. This is the convergent sequence that I'm referring for, which is the superior and the inferior. Okay, you can pick up the subsequence. You see, there are quite a few ways to pick up subsequence already. For example, this lim if lim sup. Okay, we can pick out some subsequence. And pigeonhole also can help you pick subsequence. And what else? Vista point also can help you pick some subsequence. Yeah, so there are a few ways to pick subsequence quite systematically. It's not by choice, like I want this one, I want that one, I want this. So there's some systematic way to do this. And then it proved that this systematic way can help us to prove stuff. Okay, and look at the conversion of the original sequence. Okay. Make sense or not? Yeah. Okay, any question before we continue? Let me take a break first. Any question? If not, we resume 210.
那一种，我在国内就在中国，看见，带我那2个不要才反应，我要去跟他们打一些 meeting，去管着那些。
OK OK 好，好好，厉害吧？厉害，对，OK OK。
我这是在说，对。我为好好的，我为。那你这是长的，不要。要自己。
可是没有
是甜的，对，几块。
我没有看到，没有看到，但是我有看到有人给我看
两个相关的照片，
感觉有点短粗。
是
照理
是顺的，但是感觉好像不一样，因为我把握我都片，我帮你一张，
请吃，
你讲老师在讨论第四题吧，
我就我看了，
身心短了，
就发给
我先看了一下，然后后面，诶，
真的假的？
我讲么？我想讲么啊？然后你后面自己讲错啊，我就把开了。
他讲就这个。
把它
怎么样？我傻逼讲的是乱讲他自己两番字，没有的话两番字。
在修复，
没有，懂了。等于只是把人家的这些东西，重要东西还是
正好在修复。
所以你看到你懂不懂干啥？两数字就看来是
现在也是，还是半夜了。
半夜吃点可以啊。
没有吃过没？有啊，有半夜卖啊，卖到3点呢，真的，
卖到3点而已。
真的。
我家乡那边有一间包括店是12点开，晚上12点开到第二天早上8点吗？晚上12点开到早上8点。没有啊，是火了，很多，那每年都很多人去。
那有点
你要去吃啊，就是
约一下，
约
一下。
哦，他没请吃啊，给啊，
所以
定好时间就这样我发。definition of convergence completeness axiom， 然后 Q 是 convergence of sequence non-deviating sequence， 然后我就把 P by Q 弄成 not P of Q， 然后因为它是 or， 我只需要证明 Q 是正确的，我就可以证明这整个东西是正确的。
你要 prove P implies Q 吗？对。and then，
然后logically 我就把 P implies Q 换成 not P of Q， 然后我只需要证明 Q 是正确的就可以。
没有啊，有几种情况啊，这个东西正确了 ，Q 要正确，或者 not P 要正确，或者两个都要正确，3个情况嘛，哦。
等于说只占了一半
1/3。
啊。我去的哪一个？对，这样我大概，这样我应该是对，这样我应该。
但是我不知道是要什么。
没有，只是就是纯粹是看这个选然后来看它整个对有关。我什么？
这样的话不是什么 Key Q 都可以 work。Okay, let's start. So we trying to leave a sequence, but not completely yet. There are 2 parts here actually. Whether we want to go series or whether we want to go continuity of function. Okay. Between these 2 parts, I make a decision. We go to continuity of function first. Okay, so that means we will complete the series of continuity, differentiability, integrability, and then we will come back to series. Okay, series is the thing that we learn in calculus 2. Okay, we will maybe just prove a few more technical tests, and then maybe introduce some new tests, and then that's all for that chapter. Okay, I don't want to completely go through the chapter here because this is what we did last semester. Okay, in this semester, we just fill in the technical gap in last semester. Okay, for series, I mean. Okay, actually, even for continuity, differentiability, integrability, also the same. We will fill in the technical gap, and then we will look at a proof type of question. Okay, instead of just compute What's the integral of x squared? What's the integral of f cubed? Okay, you remember, right? You memorize, right? Increase the power by 1, differentiate the power, right? Divide by the power. Okay, but why? Why that formula works? Okay, we need to go into the definition of integrability. Using upper sum, lower sum. Oh, found out. Oh, I need to increase power on the polynomial and then divide by the power again. Okay, need to go into upper sum, lower sum. What's the definition? All right. So first thing first, okay, we will do continuity first. We will define continuity using sequence. Sequence. Again, sequence. So let's go into the realm of continuous function. All right, continuous function. So there are two words here. What is function? I think wake up already. What is function? Yeah. 功能 good. 功能函数 Okay, 函数。why call 函数啊 ？What is 函？可以包含。哇，包含。还有呢？包含got 3点水 right？ 函数 don't have. Yeah. So what's that 函呢？函这什么东西 ？Sure. Yeah. Okay, so what's function? Okay, so a function define a domain. Okay, so we will restrict our domain to a subset of R. Okay, on R means what? Means for each element in the domain, I gave a output. Okay, I associate a unique what? A unique real number. Okay, I cannot associate 2. Okay, I cannot associate 2. Otherwise, I don't know where to go. Okay, only can associate one number to one number. Okay, so this function could be many to one or one to one. Okay, it cannot be one to many. Okay, one number cannot go to many numbers. It can only go to one number. Correct? And also cannot be, of course, cannot be many to many. Okay, so we want to talk about continuous function. Okay, let's motivate a bit. What is continuous means? I think that's a very good motivation, right? Larry sent us last time. So let's use that meme. I think that meme is pretty good. Pretty decent. Fine, That's the meme. Anyone saw the meme in the slide or not? Okay, let's see which level we are at. Let's see which level we are at now. Okay, so what is I zoom this in. Okay, what's in the middle school? You think that continuous function is the polynomial function. Polynomial function are continuous. We will prove that. Okay, we will prove that. Polynomial are continuous. What else? In high school, you said that you can draw it without picking your pencil or without lifting it. It's continuous. And what else? In pre-calculus, you think that there's no hole or no jump, right? You can draw it seamlessly using a pencil without this lifting up. And what you thought in last semester or previous semester, you said that for each point C, the limit, the left-right limit is equal and then equal to the f value at that point. Okay. And if when x gets close to C, the function fx gets close to fc. Okay. And then this is what we were gonna to achieve later. Not later. Near future. Okay, maybe next week. Epsilon delta. Okay, this is finally the epsilon delta definition. Before epsilon delta, we still can't quite leave sequence yet. Okay, we can't quite leave sequence yet. So let's draw some continuous function then. And then I will motivate a bit about this definition here. So if I want to look at some continuous function like this, can I go like this or not? Can I go like this? Why? Not one-to-one, right? You see, pick this point here. There are two fx here. Okay. But this is what we learned in last semester. What we call this parametric curve. Okay, we can make it into a curve. But it's not a function, right? But we introduce a time variable to it. Okay, so when we introduce a time variable, then every point got t1, t2, t3, and then so on. Okay, then it is a function of time. Okay, so but this is not what we want to discuss now. This is in analysis 2. So in analysis 1, we will just look at something like this. Okay, so this is a continuous function, for example. So we will motivate this question is, if I want to say f is continuous at x1, what does it mean? Okay. There are two x-axis here, right? Okay. So there are two x-axis here, right? So there are two real lines. There are two real lines. Okay. In this two real line, we can consider some sequence. Okay. What kind of sequence we can consider here? Okay, we are interested at the point S1. Okay, so we can consider some sequence that converge to S1. Right, some sequence that converge to X1. Okay, so this is what sequence is. And so once we have this sequence, right, you can construct another sequence. You know what sequence you can construct? What sequence can you construct out of this AN? So let's say this AN converge to X. Okay, what kind of sequence you can construct? What other sequence you can construct here? You got an F here. What can you do with F? F apply to the sequence, right? So what is F applies to A1? Where is F applies to A1? Go to the top here. Okay, so here is your FA1. And then FA2, the next one. FA3, FA4, FF5, FF6, FF7, FF8, FX1 here. So what can you see? Can you observe anything or not? When this A1, this AN converts to S1, right? What happened to FAN? Also converge to FX1. Okay. Okay. Also converge to FX1. You see, getting closer to FX1. You can go different direction. Okay, maybe go this direction. Okay, then this is what we call left-right limit. Right. Let's say this is B1, B2, Bn. Okay. And then you can see that these B, F, Bn also converge to Fx I. Make sense or not? So you can take different one. You can take different. So you can jump away, jump across. Okay, X1. And then you can see that F of this sequence still coming around Fx I, Fx1. Okay. So meaning, let me put here. So this implies that Fan equals to Fx. So what do we want to define here? So we will define that a function, okay, a function f defined on the domain, df is continuous at a point pdf. Okay, if for every sequence, okay, if every sequence Sn in df such that it converges to P, then the sequence FSN also converges to FP. So we will say that, or subsequently, we'll say that F is continuous on the whole domain, okay, if it continuous at every point in the domain. Okay? So we define continuity at a point, okay, and then if you want to say that it continuous on the set, it means that F is continuous at every point in the set. So let's so maybe there's a lot of word here. So let's try and decode what's this definition here. So let me make some remark here. So when we say there's a continuity at a point in DF, so what does it mean? So it means that as S approaches to P, okay, Fx also approaches Fp, okay, or use the language we have just now for every sequence of DF, okay, if what? So if Sn converge to P, then Fsn also converge to Fp. So remember, what's the definition of convergent sequences now? For every epsilon, there exists an n such that for n greater than n, Sn minus P is less than epsilon. If you have this, you need to prove that for every epsilon, there exists maybe another n, okay, such that Fsn minus Fp is within epsilon. Okay, so there are two sequences controlling. Okay, controlling. One sequence is controlling the other one. Okay, so how to show something? How to show? So in this case here, how to prove F is continuous at P? Any idea? How to prove F is continuous at P? How to prove? What's the definition of continuity? How to prove F is continuous at P? What do we have to show? We want to show that Fpx Fp exists. Oh, Fp exists. Does Fp exist or not? Because P is in the domain, right? So F of P surely exists because F is a function. Okay, and then sorry, Fxn must converge to Fp for every Sn that converge to P. Okay. So this Xn, so Xn is picking from the domain, don't picking too far away from the domain. Okay. On the other hand, if you want to prove a function is not continuous at P, what do you do? What's the negation of the statement? What do you need to do? What's the negation of the statement? So this statement is true for all sequences that converge to P, right? So negation is what? There exists one sequence that converge to P, but Fxn doesn't converge to Fp. Okay, yeah. Okay, so you are using all the knowledge before about negation, convergence, right? Okay, so far any question about this definition? Any question? No? Okay, good. So let's try. Okay, let's try some example. Let's try some example here. So let's define this example then. So define an F on 0, 1. Okay, so this is a subset of R. okay, to R by what? So we do it by piecewise function. So equal to x if x is in between 0 and half, and x minus half when x is in between minus half and 1. Okay. So what's this graph looks like? What does this graph look like? So this is domain from 0 to 1, right? So let's just draw 0 to 1 then. How does this graph look like? Huh? Two parallel line. Okay, what line? Fx equal to x up to half. So somewhere like here. And then not including half here. Right? Okay, and then another line from where? Huh? Negative half to 1, where you have the same gradient of line. Okay. Okay. So which point is continuous and which point is discontinuous for f? Yeah. Only half is not continuous. Okay, so let's prove it. So we will prove that f is continuous. F is not continuous at s equals to half, but is continuous at all x that's not equal to half, where x is in 0. Okay. So how to show it is not continuous at half? You need to find a sequence such that fxn. So okay. So to show f is not continuous at x equals to half, we need to find a sequence. So we need to find a sequence that converge to half, but fsn is not converging to f half. Okay, what is f half here? 0. Okay, doesn't converge to 0. Okay, so what sequence does this? Can you think of a sequence that does this? Can you figure out what kind of sequence can converge to half? What sort of sequence converge to half? What sequence you can take that converge to half? Any idea? Huh? What n? What sequence converge to half? What sequence converge to 0? Let me ask you. 1 over n. If you want to make a sequence that converges to 1, 1 plus 1. If you want to make a sequence converge to half, half plus 1 over n. Okay. But what was okay, half plus 1 over n. So is this sequence here live in df or not? Does this sequence here live in the closed interval 0 to 1? Is it true? When n equals to 1 is 3 over 2. Okay? When n equals to 1 is 3 over 2, correct? So it's a bit too big, right? Okay, so what do? We can modify a bit, right? So when n equals to 1, it is not living in that set. Huh? Minus. Does it work? So if I take 1, I get negative half. Also not in the set. I can just make this denominator larger, right? N plus 1. So when n equals to 1, I get half. Half plus half is 1. So it will lie inside the set already. Okay. And then continue to take a smaller 1 over n plus 1. Okay, so this is a sequence in 0, 1. And in particular, we can prove that Sn converge to half. Okay, how to prove this? Either you can use definition. Definition says what? You need to take Sn minus half less than epsilon, which epsilon is greater than 1 over n plus 1. Okay, you can find some n. Or you can use limit law. Right, you can use limit law because half is a constant function. 1 over n plus 1 is a function that converges to 0. Okay, you can use limit law. So we can prove that Sn converges to half either by definition of limit, I mean the epsilon n definition, or by limit law. Okay. How about Fsn in this case? What is Fsn? Then Fsn is what? Fsn is what? So this term here live in where? It doesn't just live in from 0 to 1, right? It actually live in the where? In the subset of half to 1. Correct. Correct. Okay. So we need to use the piecewise definition of this one. Right? X minus half. Okay. X minus half. Correct. Live on this domain here. So what do? We need to take Fxn equals to half plus 1 over n plus 1 minus half, which is 1 over n plus 1. What's the limit of 1 over n plus 1? 0. But what is our f half? Also 0. Converge to 0 at this guy. Not good, huh? Not good, eh? This Fsn converge to 0. Not good. So can we change some other choice of Sn that converge to where? Half or not? Maybe we can consider minus instead. Right. What does it mean by plus? Plus meaning we consider all the points here. Okay, but all the points here, of course, by definition, you see, of Sn, it will converge to 0. But if instead we pick minus 1, what happened? If we pick minus 1 here, what happened? What's the first term? 0. Okay. Second term, 1 over 2 minus 1 over 3 is 1 over 6. Okay. So all the terms is lying on the other side of 2, of the left-hand side of 2. So on the left-hand side of 2, the function of f is increasing to half, which is not 0. Okay, let's do this computation here. So Sn equals to half minus 1 over n plus 2. In this case here, this will lie in the interval from 0 to half. Okay, but if you want to check f of Sn, you need to use the first definition of f. Okay, first part of the definition of x, which is fx equals to x. So in fx equal to x here, we get Fsn equals to half minus 1 over n plus 1. And this one will converge to when n large, this limit converge to half, which is not 0. Why? From the picture, you already can see already. If I pick sequence on the left-hand side here, the FSN should converge to half. Okay? But if you take it from the right, it will converge to 0. Okay? You don't want that. Okay. Make sense or not? Can you see the sequence directly from the graph or not? Can you see or not? Can see? Can everyone see the sequence directly from the graph? Okay, previously we take sequence here, approaching to half. And then we found out that actually this FSN also converges to 0. True lah, because this is what the graph gives you. Okay, so if you want to make some limit that is different from 0, the only hop is here, on the left-hand side of 2. Okay, if you pick sequence from the left-hand side of half, then this FSN will converge to half, which is not 0. Okay, makes sense? So you should be able to see from picture, not just a calculation of a sequence. Okay, you should be able to see from pictures. Okay. Okay, so this is about discontinuity. How about continuity? Next, prove f is continuous every point p not equals to half in 0 to 1. Okay, so what to do here? We have to prove that it's continuous at every point p not equal to half. So you need to start with any sequence that converges to p and then show that FSN also converges to FP. Okay. So what to do here? So how to prove that? So I mean, you can split into 2 cases, right? Two cases. Why I split into 2 cases? Because our function is defined piecewisely. Right. So split into 2 cases where p is greater than half and p is less than half. Okay, because this 2 function is different. Right. For p less than half, you have just x. For p greater than half, you have x minus half. Okay. So case 1. Suppose you have an xn that converges to half. Converges to p, where p is greater than half. Okay. Suppose this. Then you want to prove that. What do you want to show? You want to show that FSN converges to FP. Okay. So this is what you want to show. Correct? Okay. So so then you need to compute what is FSN then. What is FSN? When P is greater than half, right? Okay. What is FSN? Huh? So I mean, for large enough. So wait, let me draw this picture for you so that we have something to imagine about. So let's take this down. Okay. So you want to converge to some P that is greater than half. So I mean, you have P here, okay? P greater than half on one side, okay? So your sequence, I want to converge to P. What is the possibility? It might take some values here, okay, away from on the left-hand side of half, but surely it should come into the region of 1 over 2 and 1 at some point. Okay, so we will say that for large enough, then for large enough n, okay, for large enough f n, Sn will lies between half and 1. Does it make sense? Because because P is your limit. So Sn, no matter how it jumps, right? At the end, it should jump around P here, which is in the region of half and 1. Okay. So in this case here, it's good. For large enough n, this is in here, and Fsn is just Sn minus half. Okay, so Fsn become a sequence in terms of Sn. But you know the conversion of Sn. Sn converge to where? Sn converge to where? Converge to P. Okay, this guy here converge to P. And minus half is a constant sequence. Converge to minus half. But what is P minus half? It is just Fp. Okay. Does it make sense? Okay. So if you think that macam not rigorous, or seems like not rigorous. Okay, macam is seems like. Okay, seems like not rigorous. Okay, go and try your epsilon delta. Epsilon delta, because this is conversion, segment of conversion. Turn this into, for every epsilon greater than 0, there exists an n such that Fsn, when n greater than n, Fsn minus Fp is less than 2. Do that. Okay, so try exercise. Try write this proof in terms of, so I write here, try proving it using epsilon n definition of a limit. Okay, try and turn this into a epsilon n definition of limit, and then you will see what does this large enough n means. Okay, you will see what does this means. Okay, try and write down this. Okay, I will write down as well, so that you can compare. Okay, what am I doing here? Okay, no. So similarly, you can do for, so case 2 is what? Case 2 is, so this is case 1. So case 2 is Sn converge to P where P is less than half. Okay. In this case here, it's even easier. For large enough n, I can lock my n within, I can lock my Sn within 0 and half. Okay, and Fsn is what? It's just Sn. But you know that Sn converge to P. What is P? It's Fp, because P less than half. So also converge. Okay, so I try to challenge you, try and write down these proof in terms of epsilon n. Okay, and then you will see what does it mean by large enough. And I can lock my sequence within epsilon. Okay or not? Okay, okay. We got still more minutes to go. Let's look at another example. Let's look at the identity function. And let's look at identity function. So f r to r, which is s going to s. Okay, which in other words, fx equal to x. Defined by fx equal to x. Okay, so this function is even easier than what we have just now. It's something like this. Okay, this is the graph. So where does this function continuous? Everywhere. Okay, it's continuous and everywhere. So we just pick any x in R. Okay. Suppose what? We have a sequence that converges to x. Okay. We want to show what? Fsn also converges to fx. But what is Fsn? What is Fsn in this case? Sn. And then we know that Sn, by definition, by assumption, Sn converges to x. But what is x? Fx. So Fsn converges to x. Okay. Yeah, so this is the trick here. All right, so similarly, okay, we don't want to do this thing again, but I want to give you more example. Similarly, you can talk about absolute value function, okay, where this is minus x when x is less than equal to 0, and x when x is greater than equal to 0, right? So what's this graph here? So you should remember the V-shaped graph, right? V-shaped graph. So where is this function continuous? Also everywhere. Okay, so exercise. Okay, show that fx is continuous everywhere. Let's show this continuous everywhere. So you can use the argument I had just now. You can use sequence convergence, or you can go into epsilon delta and then show it with epsilon delta. I'm sorry, epsilon n. Okay, you can do that. And let me define another interesting function here. Okay, one more interesting function. So I will define fx equals to minus x when x is rational, x when x is irrational. Okay, and then this function is defined on R to R. So how does this graph look like? Anyone want to guess? Rational if minus x, irrational when it is x. When x is irrational, rational minus x. Remember we proved a theorem, right? The density of rational and irrational. So both of them are dense in real number. So every two real number, you can find one real irrational, one rational. And then you can keep doing this. Okay. So what's this graph looks like? What two line? Data. Yes, data. Two dash line. Okay, we can get some two dash line. Because at some point you need to go to minus, at some point you need to go to x. I don't know. Because you have like irrational, rational, irrational, 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 irrational. Between two real number, you can find one rational. Between two real number, you can find one irrational. So you have like rational, irrational, like mixing between. Okay, the density of rational and irrational number. Okay, so you want to guess where this function continuous or discontinuous? Yes. Continuous at 0. Yes, prove it. Oh, need to prove it. Continuous at 0 only. Okay, only continuous at 0. So try and exercise. Try and show that this is continuous at 0. Okay. Yeah. Continuous at 0. Because if you pick any other point than 0, right? Okay, for example, maybe you pick a rational point. So if you pick a rational point, your fx lie at the positive part or the negative part. Okay, depending on your rational. Okay, and what you can consider a irrational sequence convergent to the rational point. Why can I do that? Because irrational is dense. So I can keep finding irrational number close to this rational number. But the point of irrational is always on the opposite side, minus x. Okay. So you will converge to something minus of this rational point here. Okay, try and write it down. You will know what I'm talking about. Try and write it down. Okay, write down your goal and then write down the sequence of irrational to rational. Okay, does it make sense? Make sense or not? So just now we built a Cauchy sequence to irrational, right? Similarly, you can build some sequence that converge to sequence of irrational that converge to rational using the density of rational and irrational. Okay, one last thing. Hey, why there's no next class? Okay, let's do one last one and then we will take a break and then maybe we can resume talking about it or I just put it in the lecture notes. So one last one is like this. So I define a function from R to R and I will take values 1 over n if I'm a rational number, okay, m over n. So of course you assume m over n have no common divisor. And I take 0 if it is irrational, okay. So how does this graph look like? How does this graph look like? So let me show you. It looks a bit like this. Total, and then suddenly when you go to the integer value, it jumps. Because 1 over 1, 2 over 1, 3 over 1, 4 over 1, you should take 1. Okay. And then where is it continuous? It is continuous at every irrational number. And then discontinuous at every rational number. Okay, try and show you. Okay, so this is the picture of this function. Okay, yeah, so these two a bit weird function. Sometimes very useful when you go. Sure. Okay, any question? Any question before we break? Any question? Oh, great. Yeah, try and show it. I will do it in my lecture now as well. Yeah, try and work it out, see if you can prove it. Okay, can you try and convince yourself first whether it is continuous or discontinuous? And then try and show it. Yeah. All right. Then we'll see you next week.